This is May June 2025, paper 22, physics 5054. These are the grade thresholds for this exam out of 80. You can see that it's not that difficult to get an A in this, but at least let's try. So the question is about a ball dropped from the side vertical scale that is marked in centimeters. It's completely fine. A video recording shows where it is in terms of its time stamps and distance covered while moving along the meter rule. Now, this is the table given to you already. He wants you to plot these coordinates on the graph, which I've done already. You can do this by yourself. And then a straight line is supposed to be drawn between the points. So I would advise you to rotate the question paper like this, upside down, and have your palm of the hand on this side. Once you do that, then it's very easy, or it gets easy to draw this line of best fit, which is going to be approximately like this. Please excuse my drawing. Crossing through all the points like this. Please make sure that this doesn't happen, which I've done here. It should be one continuous smooth line. And once you've done that, you can rotate the paper again upside down in the proper way, and then you will have a line like this. If you're trying to draw the line from this side like this, it invites a lot of chances of error. This is just a recommendation. If you're comfortable this way, it's fine. Next question. Calculate the average speed between T0 and T0.4. What we're supposed to do is, since we're supposed to do the average speed, that will be total distance. In physics, when it's about average, you just add total into the formula, divided by total time. Writing the formula is absolutely necessary. The total distance covered in that time frame or in that time period is up to 0.4. From the graph is 78 centimeters. Be careful about the unit. So this is 78 centimeters divided by the time taken is 0.40 seconds. This will come out as 195 centimeters per second. You don't need to convert this into meters per second. Why? Because it's already given as a unit, so there's no point converting it back. Be careful. Describe how. Use the figure. Now, if he mentions that you're supposed to describe how to use the figure, then please refer to the graph, what you're going to do with the graph. To determine the speed of the object at t0.4. You see, if this is a distance time graph, the gradient of this graph represents speed. Now, that's exactly what we're going to write down, that if you want to determine the speed, we're going to talk about the gradient. But for a curved line, what will be the gradient? So for this, we draw tangents at those points where we want to find the gradient. So at 0.4, the tangent will go something like this, touching the line only at one point. This is, of course, a gross approximation. And then we use the coordinates on that line to find the gradient at this point. So that's exactly what we've written down here. We describe the process. So draw a tangent at 0.40 seconds, and then the gradient of the tangent, you have to say the gradient of the tangent gives the speed, or helps us calculate the speed. As a ball falls, the expression acceleration of the this question has been a very repeated question in terms of its occurrence. So let's try to see what's happening. So he says, explain the terms of forces acting. When he says about forces acting, you have to give their name and what is going to happen to them, or what is causing them. So let's talk about a falling object. It has weight on it, it has drag on it. What's going to happen with them? So we talk about the weight being constant. So as a resultant force, which is F equals to ma, this becomes weight minus drag equals to ma. W will not change. It's a drag of the air resistance that's going to change. So as the object falls, the speed increases, and we know that drag depends on the speed of the object. The faster you try to go, the more drag you experience. So we're going to refer to that information here. So increasing the drag, this reduces the resultant force. So if you increase the value of d, overall the answer is going to decrease. When the resultant force decreases, the acceleration's value decreases because mass is constant, it's not changing. So eventually, the resultant force is dependent on the acceleration, or controlling the acceleration, hence leading to a smaller acceleration, which eventually becomes zero at terminal velocity. When does that happen? When weight becomes equal to drag. When they become equal, the answer on the left-hand side becomes zero. Mass is not zero, but then acceleration becomes zero. So that is the answer in terms of forces acting. Next question, he says, describe the appearance of a distance time graph when the acceleration of the ball is zero. So it's going to be a straight line of constant gradient for a distance time graph. We can see that Not here, but it's going to look something like this. The graph is going to look something like this, straight line. When the gradient is 0, the speed will also be 0. Question number 2, he says, define power, that's work done per unit time. The efficiency of the motor is 70%. Now the power output, useful output power is given as 600 watts. If we draw the Sankey diagram, it's going to look something like this. The useful output power is 600 watts. The machine is 70% efficient. He's asking us about the input power. The formula is going to be the efficiency, which is 70%, equals the useful output power, which is 600, divided by the total input power multiplied by 100. Now be careful about converting this by dividing this with 100. Then this comes here and this goes there. So this becomes input power equals 600 divided by 0.70. So the input power is going to come out as 857. Yeah, 57 watts. But up to two significant figures, this will be 860. The forklift left the truck 50 kg vertical distance. This work done. So work done. This is an indirect question asking you about the gravitational potential energy, which will be GPE equals mgh will become 50 multiplied by 9.8 multiplied by distance, which is 2.3. This comes out as 127 joules, which becomes 1100 joules up to two significant figures. Time taken for the lift to lift this load. So the effective output power that is in your axis is 600 watts. So since we want to find the time, the equation that links energy or work done with all of this together is power equals energy divided by time, or work done divided by time. So power is 600. The energy transmission required or the work done requires was 1100 divided by t time. Time is going to come out as 1.83 seconds, which is going to become 1.8 seconds up to two significant figures. Describe how the energy is transferred to thermal store as the load is lifted. So there are two options to this. Electrical windings in the motor get heated up when current is transferred through them or controls through them. The other option is heating of the moving parts due to friction. So there are a lot of moving parts when the lift does this, when it's moving up. So the friction in this column or any other place in the moving parts is going to remove energy. So it's going to be a very simple answer in this. Question number 3 is about pressure. Tire inflated. If we find the force exerted on flat tire is 1350. Calculate the pressure exerted by the flat tire on the road. So pressure formula is force over area. Force is 1350 divided by area is given to you in already meter squared. So this will be 0.0070. This answer for pressure comes out as 192857 pascals, which is going to become 1.9 into 10 raised to the power 5 pascals up to two significant figures. Air is pumped into the tire to inflate it. The increases the pressure inside. The force exerted by the tire does not change. So P equals F over A. State how the area of the pressure changes. It's not increases. It's supposed to be decreases. So if the force is not changing, as he mentions, the force is still the same. You increase the pressure. Pressure is increased, so the area will decrease. They are inversely proportional. That's why the air contact decreases. Inside the inflated tire, what is its momentum? It's simply a product of mass and velocity of the object. Using ideas about momentum, now we need to involve momentum, force, time, impulse, something like this. So force is defined as delta P divided by delta T, or rate of change of momentum. We're familiar with that. We're going to involve our answers around this. Explain why there is a force on the wall when the tire particles collide. This is a repeated question, classic question, how gas molecules exert pressure on surfaces. So the collision with the walls causes a change in momentum due to change of direction. You see, the mass of the particle is not changing, the velocity is. So if this direction the velocity is positive, this direction the velocity is negative, which causes a change in momentum due to change in direction. So that change in momentum over time, according to this formula, causes a force or gives rise to a force. As the car moves, the temperature of the air inside increases, the temperature is increasing. The increase in temperature causes inside the pressure to increase. Using idea about particle molecules, kinetic model of matter, and that temperature controls the kinetic energy of the molecules. And kinetic energy is actually the speed of molecules. Why? Because kinetic energy is half mv squared. If it's an oxygen molecule, if it's a nitrogen molecule, you cannot change the atomic mass of the atom, but you can change its velocity so that it represents or makes you feel a different temperature. That's exactly what's happening here. So we start our answer with, at higher temperature, the kinetic energy increases from kinetic model of matter. The speed increases, which in turn increases the momentum, because momentum is a product of mass and velocity. This is exactly why he asks you about momentum here, so that he can ask you about changes in velocity leading to changing in momentum later. So momentum increases, the force on the wall increases because of this formula, which is delta P divided by delta T, leading to a higher pressure in the tire, because pressure is force over area. Higher change in momentum gives higher force gives higher pressure. So all of this is combined for 2 marks question in these statements. If you write it down like this, the examiner understands that you understand, or you already have this knowledge in your head about the momentum bit and about the pressure bit. Question 4. Sound waves from vibrating tuning fork are given so and so. This is a serial microphone. Describe the motion. Describe what you would see with your eyes if the air particles are moving through sound wave from tuning fork to the microphone. So there are air particles between the tuning fork and the microphone. So they are going to move forward and backward in a series of compression and rarefactions. That's exactly what we're going to write down. So when the tuning fork vibrates, the air molecules near the tuning fork actually vibrate or move back and forth in a series of compression and rarefactions while transferring energy to the next air molecule till it reaches the mic. So the tuning fork is moving back and forth. The air molecules are influenced by this movement. They transfer the energy to the next molecule, so on and so forth. That's exactly what the mechanism is. And when the question is about describe, you will simply talk about the fact what you're going to see in terms of physics, in terms of science. Show the trace of oscilloscope, tuning fork, or confined frequency. There are 2 definitions: number of oscillations per second or number of waves passing a point in unit time. You can write any one of them. The trace shows produce 0.05 seconds. Calculate the frequency of this. So if we notice that the total time is given to you, and frequency generally used to be 1 divided by t. But if I want to do something like that in this graph, I can see that one wave from this point to this point doesn't have a fixed coordinate. So I have to revert back to another method, simply counting the number of waves. If this was time for one wave, this is 1 divided by t, then how about we count the number of waves and then divide this is the number total of time. So this is 1 complete wave, 2 complete wave, and 2.5 complete waves. This will be 2.5 waves covering a distance, or covering in a time frame of 0.050 seconds. This will come out as 50 hertz. Hertz is the unit for frequency. So that's what we're going to write down here. I've already solved this for you up top. Question number 3. It says a student here tuning observe the trail, listen to the sound. He notices the amplitude is decreasing. Now, there are 2 things with this. So there was amplitude linked to the loudness, and there was pitch linked to frequency. That's the knowledge requirement. So if the amplitude is decreasing, the loudness will decrease, which is why we say that the sound is going to be quieter, or the volume will be reduced. Next question, it says this is the original trace. There's a new situation in which it says obtained with the fork. On figure 4.4, no, not this question, a not change. The second bit, half the frequency. If the frequency is halved, in the same time frame, you should get half the number of waves. So if there are 2.5 waves previously, then right now we should get 1.25 waves. So approximately 1 wave will be completed somewhere around here. It is inspection by eye, for example, over here, and then partial completion of the wave. Notice that I am not changing the amplitude because we're not changing that. It's only the frequency that's changed. Okay, so this is 1 complete wave and then approximately 25 or quarter of a wave being covered. 3 adjusted wavefronts. This is the wavelength of the gap. The wavelength never changes. He says draw 3 wavefronts. What I would advise you to be more accurate in this diagram, although the diagram I understand is not to scale, it is completely fine. But if you use a ruler, for example, to take the measurement between the wavefronts, and then simply place your ruler here from this moment onwards, from this point onwards, and see what the measurement is. You might find one coordinate being here, being equidistant, and then another coordinate equidistant here, and then another one here. Draw 3 wavefronts, and then same thing here with measurements, and same thing here with measurements, and then it becomes very easy to draw those wavefronts. Then you just cross all the points like this, and like this. Of course, this is not very accurate. I would use a compass for this. But notice that the gap between the wavefronts and waves should be exactly the same as this one, because diffraction does not change the wavelength. It's only the refraction that can do that because of the change of medium. He says the name of the process involved, that's diffraction. Question 5. A length of wire with a variable resistor, cells in place, voltmeter. It looks like that they are connected. Yeah, this is wrong. This is also wrong, because the resistance of the voltmeter is infinite. It's very high. And the resistance of an ammeter, ammeter resistance is almost 0. If you connect this in parallel to something, it is going to cause a short circuit. And voltmeter in series means there is going to be no current at all because the resistance is too high. But anyways, that's an observation. The cells are also not connected correctly because these two are asking the current to go to the right, which is not appropriate, which is not right. The student finds the voltmeter 0 when switch is closed because there is an error. Describe all the changes that you would make. So there are going to be 2 changes. First, we connect the batteries the right way around. It could be simply that these cells are swapped around like this. So they also influence the current to go right, they work together. Or you can change the position of these cells to look the other way, to look like this, just swapping their terminals. And definitely the ammeter needs to go here and voltmeter current needs to come here. But that's what we're going to write down, that swap the locations of meters, they are in incorrect locations, and connect the cells in the correct polarity would be the right way to go. Part B with graphs. Okay, calculate the resistance of the 9 centimeter length of wire, which is line P. You can choose any coordinate on the graph, but what I would advise you is to choose a coordinate that's already exactly on the coordinate. So there are a few options that you could have tried. This is 4 and 3. This coordinate is exactly passing from the point. And the last coordinate 0.8 and 6, which is this one, which will also give you the right answer. But we generally try to take more than 50% of the line, so this coordinate does not fall in that category. A better option, again, you will get the same answer, but the better option will be to go for more than 50% of the line. So that's going to be this coordinate. By using V equals to IR, we can see that voltage available was 6. Current, according to the graph, is 0.8. The resistance is R. R comes out as 7.5 ohms at that location. Question number 2. Explain why line Q is obtained, whether line Q is obtained with a length of the wire that is longer or shorter than 9 centimeters. You see, to answer this question, we need to analyze, or we need to recall on the information that resistance is proportional or is equal to rho length over area. And in that, we are invoking the knowledge related to this, length controlling the resistance. Now, if you want to analyze these graphs anywhere in the future, pick any single point that's the same for all of them. So if you look at 3 volts and we go to the line P, it is allowing a current of 0.4 at 3 volts. But if you go to line Q, it has permitted a current of 0.6 amperes to go through at the same voltage. Now, you can notice that V equals to IR. If at same voltage, there is higher current flowing, the resistance will be smaller. So we can argue that line Q is shorter because it has low resistance. If the resistance is low, the length is smaller or shorter. And that's what we're going to argue using values from the graph. So we'll say that it is shorter because it has smaller resistance experienced or offering lower resistance. And how do we know this? Because then now we're going to refer to the diagram. We will say that in figure 5.2, at 3 volts, line Q or resistance Q or wire Q has 0.6 ampere of current, which is higher than line P at the same voltage, which was 0.4 amp. I know it's a 1-mark question, but I'm trying to teach you the technique which you can use in other questions as well. Okay? Calculate the length of wire used to obtain the line Q. Now, again, we're going to go back to this relationship, right? And we understand that this whole circuit or this whole setup is actually connected in series, right? This is resistor, variable resistor. This is the length of wire. They're in series. So the idea behind this would be that the voltage will be proportional to resistance, series rules, and resistance is proportional to length, right? So we can draw a conclusion between voltage and length as voltage proportional to length. This gives me a mathematical equation which will be V1 divided by V2 equals L1 divided by L2. I can simply use this equation to calculate this. Otherwise, you could have drawn a ratio with them, finding a constant first and then using this equation. But for 1 mark question, it doesn't deserve this much effort. So this is simply going to be 4 divided by 6 ratios of voltages equal to length L divided by 9 ratios of length. So this 9 goes to this side, gets multiplied. So L comes out as 6, which will be 6.0 centimeters. Question number 6 is about practical electricity. A fuse is connected. There's a bulb P and there's a bulb Q. That's fine. Mains voltage is given. The heater is 2000 watts, quite a powerful heater. It says there's a 5 amp fuse in the lighting circuit. 4 fuses of different genes are available. Underline the most suitable fuse for heating circuit fuse, which we are supposed to connect here. So the formula will be simply P equals to IV that we use for fuse calculation. The power is 2000. The current we don't know. And the mains voltage is 230. So the electric heater is going to withdraw approximately 8.7 amperes of current from the main supply under normal situation, under normal circumstances. Nominal current, nominal voltage, that's what we refer to that, or normal operational current. Now, I can't use 5 and 8. The reason being, because they are less than what my heater requires normally. If I install 5 and 8 amperes, now this won't be 6, this will be 8 amp. If we install 5 or 8 amp fuse, it will keep melting, it will keep breaking the circuit because the appliance needs 8.7 to work normally. Now my choice would be definitely higher than the rated current, which is 13 amp or 30 amperes. Now we're going to choose 13 amperes and we're going to remove underlines from all the other options because the examiner asks us to underline your answer. Now, why are we rejecting 30 amperes? 30 ampere fuse will be too thick. It will be too big of a reading. It will respond slowly, not as quickly as we want to, or it may not respond at all, leaving the wires to heat up and melt. So the logic is always higher, but closer to the value or closest to the value. If, for example, we had an 11 ampere fuse versus 13 amp, we would have chosen 11 amps. So it's always going to be greater, but closer or closest. And this is what I've explained here. You can read this by pausing the video, how you explain your situation, right? Describe what happens to the fuse when the circuit current is too large. It melts, it blows, it breaks the circuit. You could have written down any one of these three options. Part C says lamp P is this, lamp Q, the current draw is this. Calculate the current in the lighting fuse when all 3 lamps are switched on. You see, they are connected in parallel, right? So lamp P demands 0.26 amp of current. This is also 0.26 amp. This is 0.43 amp of current. And through this branch, all the currents are going to come from this branch, then divide into these individual branches. So that's what we're supposed to do here. He says find the total current. We're just going to add them together, which is going to be 0.26 plus 0.26 plus 0.43 amperes. This comes out as 0.95 through that branch. The rating of the lighting fuse is 5 amperes. The lamp Q is removed from the circuit. It's no longer there. Calculate the maximum number of additional lamps of type P can now be connected to parallel in the lighting circuit. So 5 ampere is your range, is your maximum absolute capability. You cannot cross this, otherwise the fuse will melt. So to 5 amp, we still have 2 lamp P's in there. So they draw 0.26 minus 0.26. We are left with 4.48 ampere of headroom. This is what is available. This is what we can still demand. Now let's divide 4.48 ampere capability to one of the lamps demand. This comes out as 17.2 extra lamps. We cannot have a 0.2 of a lamp, so we're going to round down this number, which is going to limit us to 17 lamps. this is 17 more lamps on top of what 2 lamps are already there. So in some houses, lighting circuit protected by a trip switch, which is circuit breakers instead of fuse. State 2 advantages. Now, trip switches or circuit breakers, they can be reset, reused again and again. They don't need to be replaced, and they act faster. And if there is a fault in the house wires or communication, a fault can be traced without replacement, or it can be done more quickly. You can keep checking this again and again until the fault is neutralized or is taken care of. There's one special point. These are more than one point in one statement. The reason I've written them down like this is because I want to discuss about this point. This is one of the answers in the marking scheme, that there are some breakers that actually trip when there is a difference in live and neutral wire currents. Now see how that happens is, for example, if this is the supply voltage, this is live and this is neutral. This is, for example, a fuse, and if there is no fuse, then definitely we have a circuit breaker in place. This is a switch, this is the appliance, bulb, whatever. These circuit breakers actually measure the current of the live wire and the neutral wire at the same time. What they expect is that if, for example, in the live wire there is 1 ampere of current, then there should be 1 ampere of current coming back. If they are equal or relatively balanced, then the circuit breaker does not trip. For example, if there was short circuit and the current has went through the earth wire, or is leaking, for example, through the electric shock of a human body, then the current coming into the live wire is 1 amp, for example. The current going back will be slightly less than that. It may be 0.4 amps because some of the current is leaking through the body or through the appliance. This imbalance is detected by this breaker and it trips the circuit again. These are specially designed. So I've just taken a moment to explain that this is also one of the answers, but this is perfectly fine. Even if you haven't done this, it's fine. Question 7. This question is about DC motors, and even if they hadn't mentioned this, we could have figured this out by looking at the base of the coil. And there's a battery, DC battery. We have a split ring commutator. Now, the one thing that's missing in this question is that the poles are not mentioned in this diagram. So I think that the question is going to be about that. Let's move on. It says, state the purpose of split rings commutator. They reverse the direction of the current in the coil, because when it takes a complete rotation, these point of contact go there and these point of contact come here. And we've done this deliberately so that the current in the coil keeps moving in the same direction. So eventually causing an upward force on this side and a downward force on this side. That's how your fans or air conditioning fans in your vehicles actually work. It says why we have connected the brushes. So they provide contact with the external circuit and avoid tangling with the wires. You see, if there were no brushes here, the wires were permanently connected to these terminals. As the coil rotated, these wires will start tangling at this point. So we can't allow that. So this segregation is helped or is enabled by the carbon brushes. And they're also dry lubricant in that sense, and they're good conductors of electricity. So they make sure that the external circuit has a good contact with the internal circuit of the coil. He says there's an upward force. Now we want to find the direction of the magnetic field. The direction is from left to right or from magnet 1 to magnet 2. The direction of the magnetic field is supposed to be left to right. But how do we get to this conclusion? How do we know this? It is in this direction, that this is north and this is south. You see, you need to use the Fleming's left-hand rule, but there's some information that's missing. You see, the force is given. We accept that, but the current is not given. For current, you need to look at the battery. The current release or moves from the positive terminal to the wire in this direction and completes a loop and comes back again in this direction. So it's your choice which reference point you want to develop. You want to stand on the right side or you want to stay on the left side. The answer will not change. For example, you're standing at this location looking ahead. This current is moving away from your perspective. It's going into the page, but the force is downwards. So you start using the left hand, and let's organize our hand in such a way that first, irrespective of the direction of the magnetic field, first let's figure out the direction of the current, arrange our hand and wrist according to that, and the direction of the force. So if you notice, your second finger should be pointing into the screen like this, matching the direction of the current. Your thumb should be pointing downwards. This is your thumb. This is your second finger. And now when you notice, your first finger that represents the direction of the magnetic field, remember using the left hand, your first finger should be pointing this way, and the rest of your hand will be at the back of your hand. It's not the palm, it's the back of your hand. That's an indication that you've opened the hand or adjusted the hand correctly. Now, this direction or this finger represents the direction of the magnetic field, which is from left to right. Or you could refer to magnet 1 to magnet 2. That's what I've written down here. But how do you explain this? So you talk about the current from the battery, from positive to negative. The current on the coil close to magnet 2, which I've used as a reference magnet 2, this is where we're standing, is going into the page, as I mentioned earlier. Talk about this. Is going into the page. Now talk about Fleming's left-hand rule. Using Fleming's left-hand rule, the force is downwards when the magnetic field is from left to right, which means that our answer is right. That's how you justify for the Fleming's left-hand rule. It says state what happens to the magnetic field when the rotational magnetic field, the current and the coil are both reversed at the same time. You see, if, for example, you have changed the direction of the current, it's going this way. If it started to come this way, then the rotation will also change. But what they have done is not only change the direction of the battery, but they've also changed the direction of the magnets. So the effect gets cancelled out. They both cause a reversal, which eventually causes no change in the system. Shows this distance with a force, total moment exerted, which is simply moment is equal to force into distance. Eerily similar to work done, but it's not work done, because in work done, the distance should be the same direction. In moment, they're supposed to be 90 degrees to the force. So is asking me about the total moment, which means that we are supposed to calculate the moment of both components. So let me clean this up for the next question. Now, let's notice where the distances are, where the forces are. So we can see that the perpendicular distance between the forces will be this, making an angle of 90 degrees with both forces. It's 0.15 to one side, then 0.15 to the other. We want to find the total moment. It will be 2 times the moment of everything. So it is 2 times force is 2.3. The distance is 0.15. When you calculate this, this comes out as 0.69, but the unit will be Newton meters. So moment is 0.69, unit is Newton meters. If you're not comfortable with 2, then what you can do is simply multiply 2.3 with 0.15. That's moment on the left side, plus 2.3 into 0.15 moment on the right side. Since you're adding them together eventually, for the sake of total, I just added a 2 because it's the same thing. Explain why turning effect becomes smaller, the coil becomes more vertical. So as the coil actually becomes like this, why is the moment reducing? You see, the force always stays up in this direction. So if you look at it from the side, first the coil was horizontal, the force was upwards, and the distance was perpendicular. As the coil rotates like this, for example, the force is still upwards, the force is still downwards, but the distance between these 2 lines of action of forces is actually less as compared to the distance before. Similarly, exaggerated view, completely vertical, force still up, force still down. There is no distance between them whatsoever, which is what leads to the rotation being reduced. That's what we're talking about the first point. But the second point is about the coil is actually out of the magnetic field or is not crossing the magnetic field as much as it did before, hence reducing the magnetic force or turning effect. Both answers are accurate, whichever you choose to see fit. Question B is from radioactive sources. This is a good question. Mark this question for yourself as a revision question. Always attempt this question before going through the examination. Anyways, this is a typical structure of a nuclear reactor. Is asking about the purposes of all of them. You can take a screenshot, note them down in your book, and memorize them. You see, concrete shielding is there to absorb radiation and protect workers from radiation. Control rods absorb neutrons completely to eventually stop the reaction, or control in the sense that it doesn't get too much. The heat in the reactor doesn't get too much, or all the uranium doesn't start getting abused too much, because then it will become very dangerous if a lot of thermal energy is generated in a very tiny space. Okay, moderators, they slow down fast-moving neutrons so that they are slow enough to be absorbed by uranium atoms again. And if they're slow enough, they get absorbed and the chain reaction continues. Describe what happens to the fission reaction. Now, this is a very important question. It's repeated, and the questions marking scheme is an ideal specimen for making notes from it. So, describe the process, what happens. So, a uranium hits the uranium, a neutron hits the uranium atom. This causes uranium to become unstable. Because the uranium is now unstable, it splits into daughter nuclei and releasing 3 more neutrons. These 3 neutrons go on to collide with more uranium atoms within the sample, and the nuclear reaction continues. That is our answer, right? And this is a repeated question. Please keep this in mind. Specific heat capacity, again, definition is going to use it in the next part. So it's the amount of energy required to raise the temperature of 1 kg mass by 1 degree centigrade. The formula for heat capacity is Q equals to mc delta T. If you want to write this down, then please make sure that C, heat capacity, is the subject of the formula, which will be Q divided by m delta T. Now, once you've mentioned the formula, the examiner expects you to describe what that is. So please write down what Q is, write down what m and delta T is. Although the answer is complete, but if you still feel the need that you want to write something down, then mention that Q is the thermal energy and M is representing the mass and delta T is representing the change in temperature. Because the examiner expects that if you're writing a formula, then its meaning should also be clear. Even if it is taken from the book, the examiner still demands that the meaning of all the letters is explained. So just explain whether the coolant should have a large or small heat capacity. Now, there are 2 answers to this based on their own justifications. I've gone with the first answer, which is it should have large heat capacity so that it can absorb a large amount of energy, thermal energy, before reaching its own boiling point, before becoming a gas itself, and then safely releasing it to the radiator or through the cooling systems. Or it can have a low heat capacity, so when it does get to the radiator, it can get rid of that energy quite quickly. So both reasons and logics are acceptable. Question 9, space physics. There's a comet coming in, there's a sun, there's Earth orbit, there's Jupiter. And the first question is about draw the orbits of Mercury and Mars. So Mercury will be on the inside. Please use a compass for them. Draw the circles more accurately. And the Mars will be between Earth, this orbit, and this orbit. So Mars will be here. This is for Mars, and this is for Mercury. Yeah. Explain why the common position. It's very simple. The sun is in the way, we can't see it. Now, sometimes students write down gravity here. Gravity will be incorrect. The correct answer will be gravitational attraction. But by whom? Provided by the sun. 4 positions that the comet has shown, 9.1 on 9.1, show mark the direction of the force that acts on the comet at each 4 positions. That's centripetal force, and it's always going to be pulling it towards the center of the circle. Let's get rid of this for the sake of the diagram. So when it's at this location, please use a ruler, right? Place a ruler like this in the line of sight and draw an arrow like this. And then again in the line of sight, arrow like this, then like this, and then like this. And if you want to be even more accurate than this, although it's not required by the examiner, notice what is going to be special. So this is going to be a smaller arrow, slightly larger, the largest arrow, and then smaller again. Why? Because the vector length represents how much force there is. And as it gets closer, the force increases, and as it moves away, the force decreases. That would be a special point over here. You don't need to do that, but that's something to think about. Describe how the strength of the force, as mentioned earlier, is asking about the same question. It increases from point 1 to point 3 because it's coming closer. The gravitational field strength becomes stronger and stronger. But as it moves away from P3, its distance is increasing, so the centripetal force due to gravitational attraction will also decrease. So I've given the same explanation here. You can read this. Part D proved to be a bit difficult for students sometimes to figure this out. So it says the Earth completes more orbits than the Sun, than Jupiter at the same time. There's also one more thing to notice. You see, Jupiter is further away as compared to the Earth. It also has low orbital speed. That is exactly one of the conclusions that we have for this chapter in our book. Anyways, he says, how many orbits will the Earth make as compared to Jupiter at the same time? So first, let's find out the time for Jupiter. How much time does it take? So Jupiter time will be, and the formula we're using is simply V equals to, speed is equal to distance over time. In this case, that is 2 pi r divided by t. Because it's a circular distance, it's circumference of the circle. So for time, this will simply be distance divided by speed. So 2 pi into R of Jupiter. This is 7.8 into 10 to the power 8 divided by the speed it has is 13. Same thing for Earth. It will be 2 pi into 1.5 power 8 divided by 30. Now, when we get the answers for both of them, this one, the Jupiter, is 3.8 into 10 raised to the power 8 seconds, and this is 3.1 into 10 raised to the power 7 seconds. Be careful, this is 7. And we can see that the Earth spends less time orbiting, and Jupiter just spends more time doing that. So let's figure out how many number of orbits there will be. So if we divide 3.8 with 10 raised to the power 8 divided by 3.1 power 7, how many extra orbits will there be? This comes out as 12.25. So the rounded down answer will be approximately 12 up to 2 significant figures. That is all for today. I hope you've learned something. I'll see you next time.